All right. So taking questions from you guys. I'm going to apologize in advance that I no longer have the digital version of this thing to drop into the OneNote. So I'm going to have to just handwrite things or whatever. But at this point, I would say homework questions, go multiple choice or FRQ stuff that I put on the OneNote, go packet stuff, go. Just kind of we'll raise our hands one at a time. You tell me what it's coming from, we'll find it and put it and kind of get going on that. So, Michael, would you like to start?
Yeah. Can we look at 10 and 11 on the FCQs?
Sure.
Oh, you took out a lot.
Go away, thing. I don't want you. Nobody wants you. Ugh. I don't know. Okay. All right. Sure. All right. So this is what we're looking at, right, Michael? Okay. So for 10, it says f of x equals, and it's some piecewise function. Is the function defined above? Or I'm sorry. If f is the function defined above, then f prime of -1 is some our choices, right? So this is a two-part, what I want to do on this. One, I want to make sure that the derivative exists. And then if it does, then I'm going to look for f prime of -1. Sound good? So there's three cases where the derivative would fail to exist. So if f is not continuous at -1, the derivative doesn't exist. If the graph of f meets at a corner at -1, f does not exist. Or if f has a vertical tangent at -1, so if it looks kind of like that, f prime does not exist. Everybody's okay?
Corner,
Vertical tangent, or if f is not continuous. So those are the three things that I would be checking. So on a piecewise function, you're not going to get a vertical tangent. Well, let's do a little bit better than that. All right. So if I look at this piece, that's linear, that has no vertical tangent. That piece is quadratic, that has no vertical tangent. They can't meet and create a vertical tangent, so that's out altogether. Does that feel okay? In general, that's not going to happen for a piecewise function unless it's like inside one of the pieces, and it's something like the cube root of x or something that has a vertical tangent built into it. So let's check continuity first, because that's easy. How do I check continuity for a function? The left-hand limit equals the right-hand limit equals the value, right? So we want to look at the limit as x approaches -1 from the left. And is that equal to the limit as x approaches -1 from the right? And is that equal to f of -1? So since we're continuous over our domain, I can just plug in to find my limit. So if I plug -1 in, I get 2 for the left-hand side. we'll do the same thing. We'll plug -1 in. When I do that, I get 2 for the right-hand side. And then since the right-hand side is also f of -1, we have continuity. Feel good? Okay. So we know it's continuity. Next thing I'm going to do is I'm going to figure out if we have a corner. Okay, because we can be continuous and still have a corner, right? Everybody's cool? So to check that, I'm going to calculate the derivative of f. How do I do the derivative of a piecewise function? I just take the derivative of the pieces. But I don't know if that or equals to is there, because I don't know if the derivative is going to exist at the where they meet, right? Is that okay? So we haven't determined if the derivative exists, right? So I know everywhere up into the endpoint on 3x plus 5, the derivative exists, but I don't know if it exists at -1. Same thing, if I know the derivative exists for -x squared plus 3 everywhere, but its endpoint at -1, I have to check that, right? Because I know a one-sided derivative doesn't exist, right? When we looked at the graph of the square root of x and the derivative for the square root of x, the domain for the square root of x is 0 to infinity, inclusive of 0. But the domain for the derivative for the square root of x is 0 to infinity, not inclusive of 0. So like a one-sided piece is not continuous enough to give us a derivative there. Is that okay? Now I know they hook together, we found that, but if they hook together at a corner, the derivative isn't going to exist at -1. So I don't know that's or equal to or not yet. I'm going to check it right now though. Everybody okay? So to check whether there's a corner or not, I look at the limit as x approaches -1 of f prime of x. And I want to know, is that going to be the same as the limit as x approaches -1 from the right of f prime of x? Well, that's 3, and that's 2. Okay with how I got those? Feels good. So what am I seeing here? They're not equal. That tells me I have a corner, which tells me that that derivative doesn't exist at -1. So I plug -1 into here. There's no x, so it's just 3, right? That's a constant function. And then I plug -1 into there. -2 times -1 is just 2. Does that feel good? So I know, in fact, that this is strictly greater than, because the derivative doesn't exist at -1.
So if they were like say they were both 3, then it would be 3.
Then the derivative of -1 would be 3, and it would be or equal to on the piecewise. Does that feel okay? So again, like we're basically just plugging in the endpoints and seeing if they work out. But I want to explain, like, so you understand, it makes it easier to remember what to do if I'm talking through and like giving a really deep, heavy explanation as to what we're doing and why we're doing it. So it's just not like memorizing a process. Like if you understand what we're doing, it makes it, at least for me, massively easier to remember what to do if I know why I'm doing it. Do you know what I'm saying? Sorry that took a long time. Ideally, like if you know what you're doing, what to do, that's quick, right? Because nothing was complicated that we did there. It's making sure we understand the why that I spent a lot of time talking through. All right, for 11, I'm going to do my work for 11 in a different color. So if you go back and look at this, it's clear what work goes with what, since I was kind of all over the place and used a lot of space. It says the table above gives the value of differentiable functions f and g and their derivatives at x equals 1 if h of x equals 2 times f of x plus 3 times 1 plus g of x, then h prime of 1 equals what? So I'm going to start by just calculating h prime of x. To do that, I'm going to do a product property since I have two functions multiplying to each other. So I'm going to have the first function, 2 times f of x plus 3, times the derivative of the second function, 1 plus g of x, and then plus the second function, 1 plus g of x, times the derivative of the first function. So far, so good? Okay. Now, the derivative of 1 is 0, and the derivative of g of x is just g prime of x. So far, so good? Similarly, over here, the derivative of 2f of x is 2f prime of x, and the derivative of 3 is 0. So now if I want h prime of 1, I want 2 times f of 1 plus 3 times g prime of 1 plus 1 plus g of 1 times 2f prime of 1. So far, so good? Okay, I'll go to my table. F of 1 is 3. G prime of 1 is 4. G of 1 is negative 3. And f prime of 1 is negative 2. And then I just kind of grind out my answer here. So I have 6 plus 3 is 9, times 4 is 36. 1 plus negative 3 is negative 2, times negative 4 is negative 8. So I think I get 24. Oh, sorry, 28. Oh my goodness, no. That's negative 2 times negative 4 is positive 8. Jeepers creepers, 44. The hardest part was the arithmetic. Does that make sense as to what I did there? So again, like, it's a great way of making sure you can do the product rule without actually giving you anything to like differentiate itself. So this becomes a problem you can't put into your calculator and do anything with. We'll eventually show you how you can do like the derivative of any function at a specific x on your calculator and just have it spit out the number for you. This is a way to ask that question without you being able to do that. Feels good?
Yeah.
Okay. Who's next? Again, could be homework, could be MCQ, could be FRQ, could be the packet we gave you guys last time. Alex.
You do
18B from the packet. Yup. I'm going to warn you right now, though, it's yucky.
Yeah.
All right. So, as this is currently written, we do not know how to take the derivative of w plus 3 to the 5th. We will on Friday, but we don't know how to do it today. So what I'm going to do is I'm going to start by expanding out w plus 3 to the 5th. So to do that, I would use the binomial expansion. So like 5 choose 0, w to the 5th, 3 to the 0, plus 5 choose 1, w to the fourth, 3 to the first, and then just kind of keep on going. Does this look familiar, Alex?
Yeah.
Now, do you need to remember this thing? No, I'm not going to put something where you have to use the binomial expansion that's like this annoying on a timed test, because that's just like cruel and unusual punishment, right, Mr. Kulik? I can't be expected to like take 10 minutes to do this like stupid binomial expansion and still have time to finish this thing. I would not do that to you. All right, so let's grind this thing out. 5 choose 0 is 1, and then 3 to the 0 is 1, so I just have 1 times w to the 5th. 5 choose 1 is 5, and then 3 times 5 is 15, w to the 4th. 5 choose 2 is 10, and then times 3 squared is 90. And then 5 choose 3 is also 10, and then times 3 squared is 270. 5 choose 4 is 5, and then times 3 to the 4th. 5 times 81 is 405. And then 5 choose 5 is 1, and 3 to the 5th is 243. So that's what I'm really going to be doing. Does that feel okay there? All right. So because of like the size of this problem, I'm going to just call this top part like f of x. I'm going to call this part h of x. And I'm just going to calculate the derivative of f and then the derivative of h. So I have something like that, right? So G prime then is going to be the bottom. Actually, let's do the whole thing, I guess. Times the derivative of the top minus the top derivative of the top. You know what? This sucks. Hold on a second. We can do better than this. Here's how we're going to do better. This piece right here is factorable. Now, I would not expect you to factor this, but it's going to make the simplification like massively easier if I just factor this right now. That's 540W.
Isn't that just the derivative of it? Of w plus 3 to the 4?
Kind of. It's a little bit more complicated than that, because if it looked a little differently, maybe not exactly. But we'll talk about that tomorrow, and it'll become super clear and be like, oh, Mr. Kulik, I wish I knew this 2 days ago. All right. So we have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared, right? If I look at the top, I notice I have a greatest common factor of w plus 3 to the 4th. I can factor out. which is super cool because I can just do that reducing. And then I just need to distribute things through. So at the end of the day, we're going to have negative 2w cubed plus 9w squared over w plus 3 to the 6th. And that's like a lot less annoying than dealing with the foiled out versions. But you would not have been wrong. I mean, that's what you would have had to do with where we're at, is to just foil everything out. And it just is like atrocious. And then try to factor back. But tomorrow, a problem like this will be much easier. Does that feel okay, Alex?
I was just wondering
if there was a better way of doing it than like brute forcing it. Not really with where, I mean, yes, but not right now is the answer there. Paulo.
Can you do 21?
21 MCQs coming up. Yes. Yes. Yeah. All right. So we have f of x equals the piecewise function, yada, yada, yada. Let f be the function defined above where c and d are constants. If f is differentiable at x equals 2, what is the value of c plus d? So my goal is going to be to solve for c and d, so I can add them together. To do that, I'm going to have to create a system of two equations. So to get my first equation for my system, I'm told that f is differentiable. So that also means that f is continuous. Differentiability always gives you continuity. The reverse is not true, though. So because f is continuous, I know the limit as x approaches 2 from the left of f of x equals the limit as x approaches 2 from the right of f of x. So I can say c times 2 plus d equals 2 squared minus c times 2. Is that okay right there? So I've just plugged 2 into both pieces and set them equal. That allow me to say that, let's see. If I have 2c plus d equals 4 minus 2c. If I add the 2c to both sides, I have 4c plus d equals 4. So far, so good. I'm then going to calculate f prime of x. Again, the way we do this for a differential or a piecewise function is I just take the derivative of each piece. So the derivative of cx plus d is just c. And the derivative of of x squared minus cx is 2x minus c. And I know, since I'm told it's differentiable, I know that or equal to goes along with it. So that's not a question this time like it was, Michael, for yours, where we didn't know if it was differentiable there or not. Here we're told it is, so we can just keep the inequalities the way they are. And I can say the same thing then, that the limit as x approaches 2 from the left of f prime of x has to equal the limit as x approaches 2 from the right of f prime of x. So I have c is equal to 2 times 2 minus c, or 2c equals 4, which I can solve for and get c equals 2. I put that back in here, and I have 8 plus d is equal to 4. So d is negative 8. So c plus d is 2 minus 8. Oh my gosh, that's not 8. That's negative 4, you dodo. Is 2 minus 4, so negative 2. Should be my answer. Does that feel okay as to how I did that?
Yeah, trying to figure out.
Yeah, so again, the key observation there was knowing that differentiability also gives me continuity. That's how I'm going to get the second equation. If you just started by taking the derivative, you would have gotten your answer for C, and then you would have, what am I going to do with that? You need that extra piece, that differentiability gives you continuity. You're seeing how useful that continuity concept that we talked about from last test is, that it's popping up kind of over and over and over again in these problems. It's an important concept. So knowing that definition of what continuity gets you, gotta have it. Yeah, no problem. Who's next? I'm happy to keep going. If there's follow-ups on any of these, if it's my explanation is not thorough enough, please jump in, chime in, and let me know. Michael K., you're up again.
Can we do number 13?
From the multiple choice?
Yep.
Sure. Yes, you may. All right. So it says the graphs of two differentiable functions, f and g, are shown above, given p of x equals f of x times g of x. Which of the following statements about p prime of negative 2 is true? So I'm going to start just by writing what p prime is. So that's like f times g prime plus g times f prime. Sound good? So p prime of negative 2 is going to be f of negative 2 times g prime of negative 2 plus g of negative 2 times f prime of negative 2. Oops. Now, all it's asking for is if this is less than 0, equal to 0, greater than 0. So all I'm going to do is look at the graph and kind of see if the values are positive, negative, or 0. Sound good so far? So if I look at negative 2, so f of negative 2 is 0. G of negative 2 is a negative value. So far, so good? Okay. If I look at G prime of negative 2, if I draw the tangent line, that's got a positive slope to it, right? So I know that's a positive number. If I look at F prime, that's going to be the tangent line on F. That's also a positive number. So I have 0 times a positive, that's 0, plus negative times positive, that's negative. 0 plus negative is negative. So I know that's less than 0. Does that feel okay?
Yeah.
So the key idea there was like, what am I gonna do for these derivatives? And the fact is that I don't care what the number is. I just need to know whether it's positive or negative. And I can just look at the slope of the tangent line and use my eyeballs. And it's, that's the key to getting it. But you have to remember to do the product rule to start it, right? The common mistake would be to just say, oh, the derivative of p is f prime times g prime. Don't do that. Does that feel okay, though? All right. Who's next? Happy to do more. Fire away. Boom, 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 boom. Yes, Elena. 23? Okay. What? If we've already done it, I'll tell you. We haven't done 23. You want to do 23? Yes, please? Yes, please. Let's do it. All right. Says the function f is differentiable and has the values shown in the table above. Both f and f prime are strictly increasing on the interval from 0 to 5. Which of the following could be the value of f prime of 3? So if I know that the derivative is increasing on the interval, what I'm going to do is I'm going to calculate the average value from 2.8 to 3 and the average value, or I shouldn't say, the average rate of change from 2.8 to 3 and the average rate of change from 3 to 3.1. And I know that the derivative at 3 should be somewhere in between those two numbers. Cool with the plan? To calculate the average rate of change, that is just slope. We'll just say m. So that's going to be 45 minus 39.20 over 3 minus 2.8. And then other one is going to be 4805 minus 45 over 3.1 minus 3. So I'll go ahead and grind this through on the old calculator here, because this is one where the arithmetic looks pretty annoying to me, although still doable by hand, I guess. I get 29 for the first one. So right away I know that 20, 27, and 29 are all out, because the slope has to be getting bigger than what it is there, right? So if I do the next chunk, I have 4805 minus 45 over 0.1. That's 30.5. So the value in between those is 30. So that's what I'd want. And again, the piece that tells me that it has to be in between those two is that it's strictly increasing. Yes, Michael.
So it's just like a number that's in between, it's not like necessarily like the average.
Correct, because it says could be. It doesn't say what is, just saying what is a possible answer. Right? So if you did the average, that could be a possible also, but it's not on the chart. Or not on the list of possibles, right? So because it just says could, you have to be like, okay, maybe not the answer I would have given for the approximation of it, which I think if you were to approximate f prime of 3, that would be the way to do it, would be to average 29 and 30.5 that's the way I would approximate it. I think that's your best approximation from the given information. But that's not what it asked for. It says what could be the value. Does that make sense? And like the subtle language difference there on how to read that. You gotta be careful with like could. That's a nasty word in AP Calculus. Maybe. Although there'll be some. Yes. Yeah, I mean, that's a common type of question. Is like, which of the following could be true? You know, like you've seen a couple in the multiple choice, I think, where it's like, here's a list of things. Like, you know, here's a situation, here's a bunch of statements. Which of the following statements could be true? Like 1, 2, 3, 1 and 2, 2 and 3, 3 and 1, all of them, none of them. You know, like that kind of a question is super common. Which you're like, sweet. You got, who's next? Who's got some more? Fire away. Jennifer. 39. Yeah, we're getting deep into it. Oh, this is an annoying one because it ran over on 2 pages. I can't help it. The MyAP site, when you make one of these assignments or whatever and then you publish it, it just does it for me. It doesn't, doesn't do anything reasonable like have a hard page break so you have a full question on 1 page. Yeah. All right, let f be the function defined by f of x equals yada, 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 where b is a non-zero constant. Which of the following is an expression for f prime, the derivative of f of x? Okay. So since we're told b is a constant, we can treat it just like the number 5 or something, right? So if I'm doing the derivative of f prime, I'm just going to go term by term. So the derivative of bx squared is just going to be 2bx, where I've just ignored the b and just done the derivative for the variable part. So far, so good. And then the derivative of 3bx is next. Well, that's just going to be 3b. The derivative of b squared is 0. Why is it 0? Because b is a constant. We treat it just like a number, right? There's no variable on it. So far, so good. And then I'm going to think about 1 over x squared as x to the negative 2, so I don't have to use a quotient rule on that. So that's going to be negative 2x to the negative 3, or negative 2 over x cubed. And so if I look, all of these have the 2bx. This doesn't. That's out. All of them have the plus 3b, so those are all good. And then this one doesn't have the negative 2 over x cubed. This one does. Oh, this one has the extra b squared. That's not what I want. Does that feel okay, Jennifer? Next up is Alex. Oh, on that one?
Yeah.
Sure. I don't have a physical copy of that left anymore either, or a digital copy of it either. Do I still have a Thought I still had extras, maybe. Oh, okay. I'll take it then.
I did the first one, I still have. Yeah.
Okay.
Yeah.
Okay. So we have.
I made a mistake on the worksheet. I'll get that.
Okay. We have this function f. We're told k is a constant. It says for what value k, if any, is f continuous at -1, x equals -1. So we have if f is continuous at x equals -1, the limit as x approaches -1 from the left of f of x equals the limit as x approaches -1 from the right of f of x, which equals f of -1. So the limit from the left is going to be this. And since that's a continuous function over its domain, I can just do a direct substitute in there. I'll save that. And then the right-hand limit is going to be here. So again, continuous function, so I can just plug -1 in. And then, oops. And then this last part is here. So again, I just get that same thing. So this is the part that I want. So I have 3 plus k equals 1 minus 5. So 3 plus k is -4. So k would be -7. Again, this was the key, is remembering our definition of continuity and what that gets us on how to write the equation. And that's something you should state, right? Because we're continuous at -1, we can say this. You know, even if you don't have the limits in there, if you at least have the equation justified as to you got it from continuity, that's better than just writing the two things equal when it's like, why are they equal? All right, part B says, assume k equals your solution to part A. Determine where f is continuous. If a discontinuity exists, classify it, show your answer, or justify your answer and show your work. Okay. So I'm going to say, I know f is continuous on the following intervals: -∞ to -1, -1 to 2, I think that was supposed to be -1 to 1. There's a typo there on the inequality because it wouldn't make any sense otherwise. There and here, because those pieces of my piecewise function, well, let's just say f of x, that's a lot less writing, are continuous over their domains. So that's most of f, right? Just because I have a polynomial, and an exponential, right? Those are all continuous functions. I know f is continuous at x equals -1 by part A. So all I'm left with is checking +1 and +2. We'll check the limit as x approaches +1 from the left. See if that's equal to the limit as x approaches +1 from the right. And see if that's equal to f of 1. So from the left, I'm using x squared minus 5. From the right, I'm using 2x minus 4. And it is equal to 1 at x squared minus 5. But what do I see here? I see -4 and -6. Those are not equal, right? So we know we have a discontinuity at x equals 1. And because what's happening is, like, the left-hand side is going into like -4, I guess like that, and the right-hand side is going into -6. This is a jump.
Why are we testing
There's a typo on the sheet on that second inequality. -1 to 1 is what that should be. It doesn't make any sense if it's a 2 there. That's just, I think didn't proofread very well. And we say it's a jump because the left-hand limit does not equal the right-hand limit. Now we need to check at 2. That's the other possibility. So we'll do the same thing. We'll do the limit as x approaches 2 from the right, and see if that equals the limit as x approaches 2 from the left, and then see if that equals f of 2. 2 from the left is -2 times 2 minus 4. From the right, that's 2 to the 2, or e to the 2 minus 2 minus 3. And then that's the same thing here. So that we already saw is, that's going to be -8. E to the 0 is 1. 1 minus 3 is -2. So we saw that again. So we know we have another discontinuity at x equals 2, and it's a jump. Again, because the left-hand limit doesn't equal the right-hand limit. Does that feel okay as to what to do there? So again, I was really thorough with my explanation. But again, the wording of the question asks, where is it continuous? So I'm going to start with all the freebie stuff. Like all the continuous function pieces are going to be continuous, except possibly at the endpoints. One endpoint was given to me for free in part A. I'm just left 2 endpoints to check. So I just checked for continuity at those 2, and I saw I failed both of them. Does that feel good? Cool. AJ, will you pass this back to Alex? Elaine. 43. Yes. Let's get it. You guys are asking good questions. These are all like tricky pieces that we really have to make sure we're using, like our definitions and everything pretty carefully. Okay. So it says the table above gives the values of the differentiable functions f and g and their derivatives at values of x. If h is the function defined by h of x equals f of x times g of x plus 2g of x, then h prime of 1 equals what? Well, we saw one similar to this before. We're going to start the same way. I'm going to just do the derivative of h to start. So here I have to do a product property. And then here, the constant comes out front. So I have that. Elaine, is that okay? Okay. And then we're plugging in 1. So I have f of 1 times g prime of 1 plus g of 1 times f prime of 1 plus 2 times g of 1, or g prime of 1, excuse me. And I'm going to go to my table here. So I'm just looking at this row. That extra row is not helpful to me. So f prime of 1 is 2. G prime of 1 is 3. G of 1 is -5. F prime of 1 is -4. And then g prime of 1 is 3. So I have 6 plus 20 plus 6. That's 32. Why in the beginning did I'm sorry, somebody rustled and I missed what you said. Why did in the beginning I added what and what? So to do this, I did the product rule. That's where this comes from. And then for the other piece, I can just do that directly. Is that what you're asking? Do you see it now? Yeah, I just did each derivative separate, right? Because I can do the derivatives, or that differentiation operation distributes through addition and subtraction. So the first piece I can do by itself, and the second piece I can do by itself. The first piece required the product property. The second piece, that's just a constant, so I can just pull the constant out front and zap the derivative for g by itself. Does that feel okay? These ones are good ones because it really makes, like, you have to really know, like, the big rules, not the shortcuts, but like, how can I manipulate a derivative and how can't I? Which are nice, right? And then the calculation is really easy without a calculator if you're able to get to the spot. Yeah, Liam. Yes. Michael. 22?
Yeah.
Sure. And just kind of as I'm inserting this guy in here and we're doing this, I want to let you guys know I did put the answers for the multiple choice and the free responses in the OneNote here this afternoon. So if you haven't checked it out lately. Oh, this is so sneaky. Okay. This one might not even be one we're supposed to be doing yet. Okay. Yeah, we can do this. All right. So I recognize, tells me, suppose that f is an odd function, i.e. that f of negative x equals negative f of x for all x. Suppose that f prime of x naught exists. Which of the following must necessarily be equal to f prime of negative x naught? So when I say an odd function, what do you think of? Like, what's an example of an odd function? X cubed, great choice. And I know that's right because f of negative x, oops. And if I multiply three negatives together, I get a negative. And that's the same thing as negative f of x, right? So if I do the derivative of x cubed, what do I get? 3x squared. What kind of function is this? Even. And I remember for an even function, that would be f prime of negative x equals f prime of x, right? So here, I should pick this one. Because when I take the derivative of my odd function, it's something like 3x squared. So it's going to give me an even function. So this property needs to hold. Now, there's a better way of doing that using the chain rule that we haven't learned yet. But you knew enough from like your pre-calculus course about odd and even functions to like, let me just do an example with an odd and an even and see what I get. Would have been realistic to do that. Maybe not nice, but realistic, especially in like a non-time setting where you have a chance to like remember what odd and even looked like. Michael, does that feel okay?
Yeah, if at the end where it says if it was necessarily be equal to the derivative of f to the negative x subscript 0, like if it was a positive, wouldn't it still be a?
Yes. Yes. Who's next? Happy to keep going. Like, I'll do calculus all day long. You know, I'm a big math-fueled robot over here. Paulo, is that a hand or you pulled it back?
Maybe 44.
Sure, 44. Multiple choice still, I'm guessing, yeah? Okay. Oh, these are good ones. Where we give you the pictures. The graph of the linear function f and the linear function g are shown in the figure above. If h of x equals f of x times g of x, then h prime of 4 equals what? Well, again, we'll start by taking the derivative of h. Hopefully by this point you recognize that's a product property, Mr. Kulik. So we're going to do h prime of 4, so that's f of 4 times g prime of 4 plus g of 4 times f prime of 4. So f of 4, let's see, is right here. That's 2. G of 4, that's right there, that's 1. Now, since this is a straight line, the slope for f is going to be the same as the derivative for f at any x. So if I look at f, I go 1 over and 1 up. Well, that slope is 1. If I look at g, I'm going like, let's see. I'm going 2 over and then 3 up. So that's going to be like 3 over 2. Does that feel okay with you guys? And so I get 3 plus 1, which is 4. The key there was recognizing how am I supposed to be getting the value for the derivative out of this graph? If even part of the graph, a section of the graph is a straight line, the derivative on that section is the same as the slope on that section. So you could use the slope formula, or you can count grids and just do rise over runs. Either is fine. I like to keep it simple. I'm a counter. If I have grids anyway. If I don't, I'll use a slope form if I have to, but with no calculator, I'd rather count than have to worry about adding and subtracting and dividing. Yuckarooskies. Just one more thing for me to screw up, you know? Or transpose an X and a Y or something like. But that's a good one. Should definitely be able to look at a graph and like get a derivative out of it, particularly if the sections are linear. Even if it's piecewise linear, like a zigzag, you know, like you just look at the slope on the section that you need. Still good. So let's do this. We have like 15 minutes. So if I'm looking for the derivative of f, but I'm given a graph, what do? Well, let's say, let's be a little bit more specific, at some specific value. What do? We look for the slope of f at x equals a, right? Assuming it exists, right? What would I see in the graph of f if it doesn't exist? Vertical tangent, or a corner, or discontinuity. If I see any of those three, derivative at x equals a doesn't exist, assuming those are all at x equals a, right? Okay. What if our graph of f is piecewise? What do? Well, we just look at the derivative of each piece, and then we have to check each boundary for differentiability, right? Whether that's continuous or a corner or whatever. You guys know what I'm saying? So we can just differentiate each piece and then check the boundaries for differentiability. That's a hard word to spell. If you just write it messy enough, no one will question whether you spelled it right or not, right? So by the boundaries, I mean, if I have like x is less than 1 and then x is greater than 1, 1 is the boundary between the two pieces, right? I have to check that piece for differentiability. So continuity at x, or for continuity with f, and then whether I have a corner or vertical asymptote. The corner I use f prime, vertical asymptote I use f. I could use f prime to do that too, I suppose. That's fine also. What if I have f is given as a table? So I can approximate with slope. Yep. For sure, you could do that. That's probably your best and only hope there if you have a table, right? You're just going to make an approximation. That's okay. I think those would be the three presentations, right? Give you a graph, a table, or a function. Well, I guess if it's just a regular old function. We're just going to use our shortcuts, right? Our power property or quotient property or, you know, product property or whatever. Just use our little shortcuts to differentiate. Don't use the limit definition unless you're like just a glutton for punishment and want to burn like a whole sheet of paper to do one problem. Yes?
For the piecewise
Mhm.
one, what do you mean by check the boundaries?
So let me go back and do the example here that we looked at where I think, yeah, this was first one. So when we did this problem here, Nate, we just took the derivative of each piece to get those guys, right?
Yeah.
And then I said, okay, x is less than 1, x is less than -1, x is greater than -1. I'm not sure if that should be or equal to or not yet. Just because the function f was continuous doesn't mean the derivative is going to exist there, right? Because you could have a jump discontinuity, or you could have like a corner or vertical tangent or something going on there. So I have to check -1 to see if the derivative actually exists there. So I have to check to make sure f is continuous at -1. Then I have to check to see if there's a corner by looking at the derivative, left hand, right hand at -1. And that'll also give me the vertical tangent if I look at the derivative at -1. That's what I mean. Does that make sense?
Yeah.
So all I'm talking about is deciding whether you get an less than or equal to at the boundary.
So when for number 10 it says when x is greater than or equal to -1, why does that switch?
Because when I checked for the differentiability at -1, we got a corner. So derivative can't exist there.
Yeah.
So in the derivative, it's just x is greater than -1, because the derivative at x equals -1 does not exist. It's undefined. Does that feel good?
Yeah.
Okay. So that's what I meant by checking. Yes.
If you want to find the derivative of x from a graph, did you have to use like the limit as h is approaching 0? Is that
So I would just be looking at slopes of tangent lines.
so if you wanted to find like the slope from a graph, that's like the derivative.
Sure. So if I have something like, you know, like here's my graph, and I have something that looks like, oops, like this. And say I'm worried about like, you know, my x equals a is right here. We're just going to be looking at that slope, right? Now, maybe I can calculate that exactly, given the type of, you know, the other information in the problem, or maybe it's just an approximation is as good as I need, right? Like if we went back and looked at, this problem here, right? Like this problem asked me basically the same thing, and I didn't actually need to find out what the derivative of f at -2 or g at -2 was. I just need to know this, whether it was positive or negative to do the problem, or 0. And usually that'll be good enough. Does that feel okay? Yes, sir.
So when, and the other one that we just went piecewise, when we got like 3 equals 2, and like we said it was a corner, they don't do each other, we just assume it's a corner.
Yes. If the limit, the left-hand limit and the right-hand limit of a derivative don't equal, that's a corner. If the left-hand limit and the right-hand limit of f don't agree, it's a discontinuity, it's a jump. Is that?
Yeah.
Okay.
So wait, can a derivative exist at a discontinuity?
No. So again, the three places where a derivative will fail to exist is at it if f is not continuous at a, if f has a corner at a, or if f has a vertical tangent at a.
So for 57.
57.
Last question.
Sure, we can squeeze her in. Hmm, 57. You picked the one where I have the graphs as my answer, right?
Yeah.
I have like a bunch of them. Okay. Okay.
Good afternoon, Notre Dame. Let's stop for a moment, take a deep breath, and close our eyes as we reflect on the day. Lord, have I looked to you today when I was fearful or uncomfortable? I pray that in times of trouble, you remind me of your presence and protection over me, that I am never alone and can seek comfort and peace in you. I pray this in the name of the Father, the Son, and the Holy Spirit. Amen. And before you're dismissed, if you are a student in the building or an adult, and you happen to be missing some eyeglasses, please come to the office. We have some eyeglasses here. And that's it for this afternoon. Teachers, you may dismiss if you are ready. And
Thank you.
You're welcome.
That's B, right?
So that should be B. So Nate, it should be B. The first part tells me it's continuous at 2. The second part would tell me there's a corner at 2. So my option there should be B. That's the only one that meets that.
Is there any chance you have an expo marker I can borrow?
I don't have any expo markers right now, but I bet Miss Kroll loaned me some the other day. If you knocked on her door, I'm sure she'd loan you one. Bye, girls.
But wouldn't it be like discontinuous at like A and B? So,
At what?
at this one, that one.
Right, but that's why I need this piece. That piece is telling me that I have continuity at A.
Oh.
At 2, right? If the limit is equal to the function, that's continuity. So that's how I know that, the only one it can't be is this one, if all I have is this, right?
Wait, I'm confused how that tells you it's continuous.
So the left-hand limit equals the right-hand limit.
Yeah.
Tells me the limit exists. That's what I have. X approaches 2 of g of x is the same thing as saying the left-hand limit equals the right-hand limit.
Okay.
Is that okay? So like if I say the limit as x approaches a of f of x exists, that's equivalent to saying the limit as x approaches a from the right of f of x equals the limit as x approaches a from the other side of f of x. Those are equivalent statements.
I just saw her walking that way.
Right.
Ran one out the door.
I don't know, I just don't, like, the limit of g of x, this x approaches 2 is equal to g of 2. Can't you say that when it just has the, like, the dot there? And it's, like, filled in?
Right, so if I have like this,
Yeah. And then, like, a circle, or like a filled in, yeah.
well then the limit is
Then it
equal to
would-
say 2 here, but g of 2 is 4 up there.
So that wouldn't be the same?
Would not be the same. So that's the limit exists, right? If this exists, that's just telling you the left-hand, right-hand limits are equal. If it's also equal to g of 2, then that has to be filled in. The place where the limit is the same as the value of the function. or the value of the limit has to be the same as the value of the function. And the only way that can happen is if that spot's filled.
Okay.
Does that make sense?
Yeah.
Cool. Aaron, you're good?
Yes.
Okay. See you later, dudes.